Yeah, let me get into the link. The link should be my email, right? Here.
Recording in progress.
Okay, I joined. Should I share the whole screen?
Yeah, just share the presentation and then it should be fine.
Presentations here.
I guess, whatever, yeah.
All right, great. Okay. Should I?
It works just fine.
Okay.
So it's my pleasure to introduce Dionysios, who's currently a professor at Yale University in the ECE department. And before that, he was also an assistant professor for 1 year at the University of State of Michigan.
Yeah, I'm still an assistant professor at Yale. I mean,
And before that, he did a postdoc at UPenn and another postdoc at Princeton. I guess his current interests include distributed systems, control theory for distributed systems, robust control, risk-sensitive control, and networks and communication. So please, the stage is yours.
okay, great. Let me see. Okay, everything works. So thank you very much for the invitation. So today I'm going to talk about a topic that I have been working for quite some time. So in particular, risk-constrained statistical estimation control. Okay, so the talk is going to have like two parts, one small part for statistical estimation, one small part for control. So these two problems are kind of intertwined, right? So before I start, I'd like to mention what's happened with the mouse. It's not. Whose mouse is that? Okay. Sorry about that. So I'd like to mention the people that have actually made, this work possible. Okay. So let me start with some classics, right? So from MMSE estimation, so everybody, I guess, knows this this thing. So we're interested in this kind of problem, right? Basically. So what we have here is like a random vector x, right? That you can think of as a state of nature, right? That you cannot observe directly. And what you want to do is to use available information, which is encoded in another random vector y, right? In order to estimate, right, x using an estimator that is a function of the observed information by minimizing the squared distance, right, on expectation between the estimator and the unobserved state. So, and of course, I mean, this is a very well-known problem. It has a intuitive solution, which is like the conditional expectation of x given y. This is like your optimal filter, right? And it's well known that optimality holds under very general conditions. For instance, x is merely needed to be like in L1 in order for this to hold. And it also has a geometric interpretation in Hilbert space when x is square integrable, right? Okay, very good. So, however, MMSE estimators do not result in stable prediction errors, okay? And this is a natural flaw, in a sense, of the problem itself, right? This is because minimizing the squared error in expectation ignores the statistical variability, right, of the error as a quantity, right, as a random quantity. And this results in optimal prediction errors whose volatility, right, is statistically uncontrolled, right? Okay. This is important from a practical perspective because simply what you would like to do is actually minimize this, right? You end up minimizing this, right? And these things, can be very far apart. Actually, this happens. For instance, if you have skewed data, right, and you want to do this kind of estimation, you can find examples where this is the case. And this is undesirable in problems where you want to safeguard against less probable but extreme losses, right? And this is what this workshop is about, right? And there are many examples, like in many applications, like energy and finance, which is actually the area that actually started it all, right, in the 40s and the 50s, and many other areas as well, like robotics, of course, applications, safety, communications, and networking that I work on, and so on. Okay. And so the goal, right, the question is how to design risk-aware estimators, right? And by estimator, I mean decision rules, functions, policies, right? Okay. So this is, of course, an old question. I mean, I'm not the first that I'm considering it, obviously. Sort of the state of the art in this area is what's called the risk-sensitive estimation, right? And this is the problem where you want to minimize the mean exponentiated, like squared error. I'm told that Margaret has already talked about that in the morning, right? Okay, so this is sometimes effective in the estimation problem, but has some limitations, mainly from a technical perspective. The first thing is that you need to have finite moment generating function of the quadratic cost, right? Which you take the exponentiation, right? And then you take the expectation of this. And this excludes many types of distributions, which are actually, those that incur high risk, right? So if you have like heavy tails, like in many cases, you can show that this objective is actually infinite, so it's meaningless to optimize it. While, these are actually the problems that you actually care about. And the second is that this approach frequently leads to very pessimistic solutions, and there is like a very rigorous relation of those problems with minimax estimation, which that is pessimistic by construction. Now, additionally, there is lack of interpretability in controlling the mean risk trade-off. I mean, there is a parameter in those problems, theta, right? But, you don't really what you're doing when you change this, right? The third thing is that there's no simple and general closed form solution, at least for the estimation problem at all, right? Not even in the Gaussian case. This approach does not effectively quantify risk that is induced by observations, right? And, this is a characteristic of what I'm going to talk about later. But, I'd like to mention that, there are problems where, you have ambiguous observations and you want to take them into consideration when you estimate, right? So what I'm going to talk about today is another formulation of the risk-aware estimation problem, which is given in this form, right? You try to strike a balance explicitly, right, between the quadratic cost that you had before and another term now, which appears here as a constraint, and is again an expectation, but the quantity that you take the expectation for is the expected predictive variance of the quadratic cost. So you take the quadratic cost, you think of it as a random quantity, you take the predictive variance of this given the observations, and then you take an expectation in order to make this a number. Okay. So this is a measure of risk. It's not a typical one because it's defined, using a conditional distribution here. Okay, but it's not an arbitrary quantity. For a random variable, this quantity is called the unexplained components of the total variance of the random quantity that's involved. Right here, the random quantity is the quadratic error. Okay. So of course, by doing that, we're going to have larger mean squared error. We're not optimal in the MMSE sense anymore. But on the other hand, we will have the statistical variability of the squared error under control, right? Now, why is this good? Well, we're going to show, right, that this risk-aware MMSE problem resolves virtually all technical issues. I mean, maybe not all, but many technical issues of risk-sensitive estimators, right? is fully interpretable because now you have an epsilon, you know what you're doing, you know, when you tune this. I mean, you're making this bigger and this bigger and this larger, or vice versa, right? And also admits a closed form solution regardless of the associated generative model, right? XY, which is probably, I mean, the most important here. Okay. So in order to talk more about this problem, let me consider a slightly more constrained version of it, where instead of the measurability constraint, which I have here, I replace it by the integrability constraint, right? So I assume that x hat is a function of the observations, which is also square integrable, right? Finite energy. What I'm going to do is I'm going to also enforce a regularity condition of the problem, which is that the third order moment filters of this form, right, are also finite energies. Now, this quantity is not arbitrary. It will appear in the solution of the problem. So therefore, it is kind of necessary to have it, like in order to be able to solve it, right? So it looks a bit strange, but, you know, it's necessary. Now, if you assume these two conditions, the risk-aware problem can be reformulated as a convex, right? Variational. By variational, I mean functional, right? Because I'm looking for a function here. Okay. QCQP, quadratical constraint quadratic program. And it's given by this form, right? So for the objective, I have done nothing. I have just expanded the condition, the expectation by a Tower property, and then expand. And then here, it turns out that the constraint, which is given like this, can be written in this form, right? So this is a number, right? So I don't really care about this. But here, what I have is a quadratic form, right? That involves the, which is quadratic in the quantity that I want to optimize. And you have, you know, the covariance matrix here, right? And another quantity, okay, which is like the important part of the solution. I will come to that. Okay, so since the problem is convex quadratic, we know how to solve it, right? We know what to do. And in order to solve it, we're going to assume another regularity condition, which is not on the problem in particular. I mean, that's a very general thing that we assume almost always when we want to solve this kind of problems. Given the tolerance that we have, we assume that there exists a solution to the problem such that the constraint is a feasible solution, such that the constraint is satisfied with strict inequality, right? So we're not only in the boundary, on the boundary of the feasible set, right? So if you assume that, then we can actually derive the optimal solution to the problem, which is given by this expression here, right? So we see now that the optimal estimator has a very interpretable form, right? It is the conditional mean, which is the risk-neutral estimator, biased, however, biased by a term, which is given here, which is related evidently to the third order moments, right, of the conditional distribution of x given y, right? And also what you have here is another matrix, which, of course, I don't mean division here by a matrix. What I mean is that you take this matrix, you take the inverse, and you multiply the numerator from the left, right? Okay, so this is the form of the solution. You see here the mu star, which is a function of epsilon. In many cases, it's 1-to-1, right? And is given as an optimal solution of this problem, which is concave, right? As the dual problem of the original problem, right? And this completes the optimal solution. This is a difficult problem. We don't know exactly how to solve this, but it's not really a problem because everything is regulated by this constant, right? So you can think of it as, you can think of this as the trade-off, right, instead of epsilon, right? So further, yeah, you can show that the optimal filter is unique with probability 1. I mean, this is just a consequence of the analysis. Very good. So why is this important? Well, it is because rarely we get closed form solutions like in variational constrained problems, right? And the problem did not look quadratic at the beginning, turned out to be quadratic, actually, and this is why we could solve it. The second thing is that it provides insight into the structure of the risk-aware MMSE estimation problem, right? So the fact that we actually need to bias is kind of reasonable. You expect that, right? Either bias up or down, right? But the strategic way that you do it, right? I mean, it's not obvious. And also, it enables direct comparison with a classical MMSE estimator, right? From this form. I mean, I'm just saying the same thing again. Okay. The optimal estimator depends, as I said before, on up to third-order moment statistics, right, of the problem. It involves elementary quantities, like everything is computable here using the conditional distribution of x given y, right? And is always well-defined numerically stable because this matrix is always invertible, right? Has the identity there. Last thing here is that that we can ask is when the MMSE estimator is this MMSE estimator reduces like to the MMSE, and what you can show is that if the skewness, let's say, of the distribution in high dimensions like does not appear, right? The skewness in a sense is 0, then the two estimators coincide. So, and this is the case actually when the model is jointly Gaussian. So for this particular formulation of the problem, if the problem is jointly Gaussian, then we don't need to say anything more, right? The MMSE is also risk averse in this case, or not. It's the same thing. Okay. So this is the first. This ends like the first part of the talk. So let's see how this works in a stylized problem. So suppose that we observe y, right, which is like a symbol or a received signal or something like that, which is given by the product of h times z plus w, right? So this is Gaussian noise. This is Rayleigh fading. This model is like the channel gain of a communication channel, right? And this is the signal, which is also Gaussian. And here you see how the joint estimator for z and h behaves for the risk-aware case, like in both noisy and noiseless cases, the MMSE, right, which is in blue, and the robust, which is in green. And by robust, I mean the conditional median, right, which solves the absolute value problem, the minimum absolute value problem, right, L1. Okay. So what we observe, one thing that we observe is that the risk-aware estimator actually works, right? And displays a much faster initial decrease in risk compared to the increase in MSE, right? This is important because if we decrease the variance, but we make the MMSE very, very bad, then, you know, we don't really gain anything. Now, fortunately, for this kind of problem and other problems, I mean, we can discuss this later if you want, this happens. For instance, you get like a 60% decrease in risk for a 35% increase in MSE, right? In this example, for the signal estimation, right? Okay. And we can also see that the additive noise, which is Gaussian, has indeed no effect on risk awareness for the signal estimation again, right? Which is itself Gaussian, right? This actually somehow verifies the result that we discussed before, that you know, if there is no skewness, then you cannot do anything like with risk-aware estimation, right? Okay. Now, this is another picture where we show with respect to the observation how the estimators behave, right? For the channel and the signal, right? And we see that the risk-aware estimator overestimates both the signal and the channel, right, compared to the MMSE estimator. This is expected, right? But we verify it. And the thing is that for small observations, right, the risk-aware estimator hedges, right, against the event of a deep fade, a deep channel fade, right, in order to maintain the estimate of the signal away from zero, which is actually what we wanted to do. Okay, very good. And now there are some natural questions that arise from this whole discussion about estimation. The first is, why can't the risk-aware MMSE solve in closed form? Of course, it's the structure, because the problem turned out to be quadratic, right, and non-trivial, which is interesting. And so the next natural question is, what about other well-known quadratic problems that we know, right, from the literature, that maybe we can treat in similar way? And for instance, quadratic stochastic control, right? This is like the dual problem in a sense to the estimation problem. Okay. And in fact, stochastic linear quadratic regulator, right? And let's see if we can actually consider this in that framework. So the textbook level of the stochastic LQR problem is given in this form, right? So we have like an objective where we have like the penalties for states and penalties for control. So this is like a very stylized problem, right? But nevertheless important. We assume like the fully observable case here, where the state x, like the state vector, is observed without noise. Okay. We assume a driving noise, which is IID, standard. We assume a control policy, which is square integrable, right? And is a function of what? Of observed information, which is like available states and controls up to the time that we're making the decision, right? Whatever. Very good. So a well-known and probably intuitive, right, as I say, optimal controller is given in this expression, like is a linear transformation of the state, where the gain matrix, right, is given in this form, and VT satisfies a backward Riccati. We know that. Right? I haven't said anything special. Okay, so let's see how we can induce like a risk-aware constraint in this formulation. We can do it before that, yeah. So what's the issue? Again, LQR controllers do not result in stable random state dynamics, right? In the LQR problem, my objective is to regulate the state, right? Okay. And the statistical variability, therefore, of the state penalty, which is what I care mostly about, is ignored, right? So evidently, like the optimal LQR controller is independent of the noise variability. And actually, we know that because there is certain equivalence, which says that if you solve this problem that I had in the previous slide, or a deterministic problem appropriately defined, you get exactly the same solution. Okay. Very good. In particular, what happens here as an estimation, the true state penalty can be far from the predicted state penalty up to information that you have up to the time that I'm making the prediction, right? Okay. And of course, there are many applications where you want to compensate for this kind of risky events. Yeah, robotics is everywhere here. Okay. So the goal, again, is to derive risk-aware control policies, right, that are easy to evaluate, right? Most desirable in closed form. Okay. Let's see an example. Okay. So we have a drone against the wind, right? We have this drone that is, for simplicity, moving along a line, right? And we have here wind, right? And suppose that the wind follows this standard, let's say, model where, it's zero with small probability, with large probability, 1 minus 1 over beta, but it's a large value with inversely proportional probability, right? Very good. So here, the expected value of the wind is 1, right? So it's independent of beta. The standard LQR controller that minimizes the total average displacement of the drone, right, is given by this expression, right? So what it does is that it just cancels the mean, right? However, we will show that the common sense controller of this form, right? Well, it's common sense because it has the beta minus 2 here, not because of this term. You cannot guess it, apparently, this. But we can show that this is actually optimal in a risk-aware sense, right? And explicitly accounts for the gas magnitude, beta. So how can we do that? Well, the state of the art, again, is the risk-sensitive control. I mean, there has been more things, you know, from nowadays in risk-aware control. But what I'm going to talk about mostly compares to this paradigm. So these are like the two papers that came out like in the 70s and 80s that actually solved this problem. This for the fully observable case and this for the partial observable case, right? Where you minimize again like an exponentiation of the cost, right? Of the quadratic cost. And again, you have the same problems. Again, this excludes heavy-tailed noise distributions, right? Specific of particular form, right? Which are precisely those that incur high risk. It results in a pessimistic formulation, and there is again a very clear relation with minimax control here. Okay, it's infinity, right? There is lack of interpretability in controlling the trade-off between mean and risk, again for the same reasons as in the estimation problem, this theta, right? The closed form solution here exists only for linear Gaussian systems. That is for systems which are not risky, let's say, right? If the noise is not too large, okay. There is no optimality for other, for example, skewed distributions. The problem with the drone, the previous slide is an example, right? And of course, there are other approaches for risk-aware control based on other risk measures such as the CVAR, so on, but they're not really LQR friendly. So again, you cannot find like closed form solutions. In some other papers, you know, people assume finite states and controls. That's fine, but we want to solve the problem like in closed form and have like a clear interpretation of what's happening when we consider risk, right? So the way to do this in this framework, right, is to add this constraint here, right, which is now similar to what we had in the estimation case, but now it is the expected cumulative, right, because we have a sum. Very good. One step predictive variance of the state penalty, right? So we take the state penalty, we subtract a statistical benchmark, which is the prediction, the projection, right, on the information that we have available, right? And we take square, sum, and the expectation, right? Of course, we're expecting a possibly more aggressive controller here, but the statistical variability of the state will be explicitly controlled, right? As in the estimation case, this resolves technical issues of the leg controller that I talked about in the previous slide, is fully interpretable again, completely interpretable, either in this case or the Lagrangian relaxation of the problem, where you put that upstairs, right? And also, maybe most importantly, admits a universal closed form solution regardless of the noise distribution, which now can be pretty much arbitrary. I'm going to talk about that in a minute. Yeah, the only condition that I'm going to make on the noise is that it has fourth order finite moments. Okay, so for instance, the log normal distribution that doesn't have that is heavy-tailed and doesn't have a moment generating function is covered by this because it has every moment finite, right? Okay, then I can reformulate this problem similar to the estimation case in a QCQP, now a dynamic QCQP, where this turns out to be quadratic, right? Now, this W here is the noise covariance, okay? And this M3 term, this is how we called it for some reason, is this, right? So it relates to the third order moments of the noise. So, yeah, okay. So the constraint contains information about both the dispersion and skewness, right, of the state penalty here. And since the problem is convex quadratic, we should be able to solve it in closed form. Okay, and we can do that using stochastic dynamic programming. Okay. So what's the optimal solution? It's given in a fine form, right? So you have a gain, again, multiplying the state. I'll be done. Yeah. Will be done, I guess, right? Okay. Let me continue because 5 minutes, right? So, yeah. So we have an affine form here. So we have this similar thing that we had like in the risk-neutral case, plus something that depends explicitly on the third-order moments of the noise, right, of the driving noise in the system. Here are the expressions now for the gain matrices K and L. The interesting thing here is that we get backwards in noise-inflated Riccati recursions. This VT, right, contains Q mu, right, which is given by this, right? So it's Q plus a term which actually relates the Q matrix to the, let's say, second order dynamics or statistics of the noise, right? And we also have here an optimal Lagrange multiplier that can be computed efficiently, which solves this equation, right? And this is this JR is the constraint of the problem, which because it's quadratic, right, you can actually evaluate efficiently recursively, right? So as a sanity check, right, if you set mu star equal to 0, you get the linear quadratic regulator. Okay. Now some remarks. I'm done. Okay. Some remarks. We obtain a closed form solution. This is even more rare, like in sequential constraint optimization, to do that. Therefore, provides insight, enables direct comparisons with the risk-neutral case, right? And other controllers as well, like the leg and so on. The controller depends up to third-order moment statistics, so it's skewness related. We said that is easily computable. Okay. And another important property is that it's always internally stable under standard assumptions like stabilizability.
No, so yeah. I know, but
Should I continue? I mean, just yeah. You know, I understand. So yeah, what I was saying, yeah, it's always internally stable under standard assumptions. For instance, stabilizability, detectability, positive definiteness. I'm not going to go into details here, but this is another important property. Interestingly, in Lagrangian form, you can reformulate the problem in this way, right? And here, this is, of course, like a tracking objective, right? What this problem does, right, is that it tracks, it precompensates for noise directions with skewness or heavy tails, right, which are captured by M3, right? And also penalizes state directions with both high penalty and high noise sensitivity, right? And therefore, what we show here, that's the last slide, almost, right, is that it is constrained LQR, at least in the way. No, I mean, I'm kind of done, so, you know. Thanks.
So which one can we go to? So now we have to go back to class.
Yeah.
I'm so sorry.
It's no, it's okay.
You know, no way. I'm so sorry for this double schedule. I'm so sorry.